All right, let's see. Start recording. Yeah, it's already recording. So yeah, if this is something that interests you, you could potentially look at the winter quarter next year. I mean, for this year, or typically it would be the next year. But Ben Hawkins used to make an exception, meaning if you student had done 306, he would waive the requirement and permit students to take the class. Anyway, all right. So the modern electronics era truly began in 1947. There were three scientists working at Bell Labs by the name of Bardeen, Shockley, and Brattain. They are the ones that are attributed with the invention of the modern transistor. Okay, this was known as the first point contact semiconductor transistor. All right, they showed how they could control the flow of current between between the two terminals of the transistor. A few years later, Bardeen, Shockley, and Brattain, they actually won the Nobel Prize for their creation. Okay, it was a very important invention that kick-started the modern electronics industry, and from that point on, it just exploded. Okay, sadly, as it happens most of the time, I have to refresh my memory about who it was. But these three people could not get along. Actually, two of them could get along with each other just fine, but the third one couldn't. And so they had a falling out. They actually, when they were nominated for the Nobel Prize, I can't remember whether it was Shockley or whether it was Brattain, but he said that it's just me. I just won the Nobel Prize. I don't want the other two. And then they were forced, like, okay, it's either all of you or none of you. And so they had to meet one more time on stage to accept their prize. Anyway, Bardeen, I believe, John Bardeen, is one of the few people, I think there's less than 6 people who have won more than one Nobel Prize. Bardeen won it twice for physics. He won it once for this. The second time he won for condensed physics or condensed matter physics. It's very interesting. I think he left Bell Lab shortly thereafter, went on to be a professor at a university, I think Illinois, or I can't remember which one. But he is one of the few people who has won two. Marie Curie is another. She's also won two. She's actually won one in physics and one in chemistry, I think. Well, Marie Curie, if you didn't know, she won. I think her husband also won. Her daughter also won a Nobel Prize, and her son-in-law also won. So a family of high achievers. All right, integrated circuits. So we had these transistors. From that point on, the race was on. The race was on to actually see how many components you could have. Because up until this point, you only had vacuum tubes. The vacuum tubes, even if they're small size, let's say the size of my thumb, far thumb, like a human thumb, right? So that's big. If you build a computer, which actually a computer was built using vacuum tubes, size of a room, ENIAC, ENIAC, okay? And so size of a room, every day, technicians and engineers would go in there and just do the work of replacing faulty vacuum tubes. It would take them hours or an entire day just to do that. So this was a big thing. Once you had a semiconductor-based device that could replicate what a vacuum tube does, it was a really big deal. And so people were already jump starting, like how can we take multiple components and put it all together onto one single silicon or semiconductor device. And so then the integrated circuits came into the picture. There were two actually two displays of integrated circuits. They were simultaneously working at the same time at Texas Instruments and at Fairchild Semiconductor. So Jack Kilby was at Texas Instruments. He is now widely credited with being the first person to demonstrate a working integrated circuit. Okay, this was an engineering development, yet nearly 50 years later, he was awarded with a Nobel Prize in physics. So that was, again, a landmark moment. And then, of course, we had Noyce and Moore at Fairchild Semiconductor. Noyce and Moore at Fairchild Semiconductor also developed, the integrated circuit independently. Noyce, Moore, And so Robert Noyce, Gordon Moore, I can't remember the third one. Why can't I remember? The third person. They all joined forces and founded a company called Integrated Electronics. That's still in existence today. Intel, Integrated Electronics. And that's where the name comes from, because they integrated large number of components onto one single microchip. All right, so integration simply states complex circuits on one single microchip. Let's see. And Robert Noyce actually had no connection to Cal Poly, but the administrators who were working just a few years ago, somehow, I don't know how, they worked out a deal where his widow donated a large sum of money to establish the Noyce School of Computing. And the way it benefits you is that the Noyce School of Computing spent upwards of $250,000 to refurbish this classroom. Isn't that enough? Typical classrooms would not be upwards of quarter. This was completely refurbished from, from the bottom up. So the carpeting that you see, everything's brand new all the way up to the lab benches. Each of these lab benches is probably about 10 grand. Easy. 10 grand easy. All right. As we have gone along, I want to show a couple of charts. This is the IC density, how complex these circuits have become. If you have taken 113 here, whether you have taken 113 or not, sorry, not 113, 143, you've seen PCBs, right? Printed circuit boards. Yeah, printed circuit boards are nothing but a bunch of components, right? If you take a simple flashlight, what does a flashlight have? It has a battery, which is a source. It has a light bulb or an LED, which is a load, and you have a switch or a wire that's connecting everything, right? Now, if you take the same thing and mount it on a PCB, your battery could be embedded on top of a PCB. The wires, instead of being a loose wire or a metallic strip, is now a two-dimensional wire that looks as if it has been printed on the board. All it's doing is it's taking a connection from the battery and it's going all the way to a switch, and from a switch, it's perhaps going to a surface mount LED, right? You press the button, wire makes the connection, light turns on. So PCB is nothing but a collection of components and a bunch of wires, right? If you take that exact same PCB and instead of having individual components and connecting them with wires, what if you instead grow them all at the same time on a single piece of semiconductor material? That's what a microchip is. That's all it is. A microchip is a micro version of a printed circuit board. Instead of taking a component separately, you're simply creating those components all at the same time. The wires are automatically, well, not automatically, but they are created in there. Like a PCB, they are laid out. It's a metallic structure that is laid out. Okay, so a microchip is nothing but a micro version of a printed circuit board. And over the years, the number of components that you are able to fit onto one single microchip has grown exponentially. It shows kind of like linear here, but it's like just unimaginable how many components we can now fit on the size of a small 1 millimeter by 1 millimeter microchip. So this just shows you how the feature size has changed as the years have gone along. Feature size, by the way, refers to the smallest dimension in your design. That's what is known as a feature size. So the smallest feature size is 1 micrometers, then your chip or your design is said to have a feature size of 1 micron. And then, of course, microprocessor complexity has grown exponentially. More often than not, it does follow Moore's prediction. There's something known as Moore's law. Gordon Moore predicted, I like to call it a prediction or a theorem, because it's not a law. Law is inviolable. It's not kind of like a law, it's a prediction. As somebody who came after him actually named it as Moore's law. Essentially what it states is that the number of transistors we can fit onto one single microchip will essentially double every 24 months. And that prediction has held true all the way up until modern times. But we are now kind of like hitting the limits of what we can do physically. Okay, we are now approaching the size of atoms. It's just insane how small feature sizes have gone, and how many transistors we're able to fit. All right, unit prefixes. As engineers, we work with very large range of devices on both ends, the smallest of devices and the largest of devices. And so we have unit prefixes to express how large or how small the devices are. I don't think it's a fire alarm here, is it? I think it's a car alarm, yeah. I was about to say somebody's bike, perhaps. Yeah. That's how my motorcycle would sound at 2 o'clock in the morning. Yeah. All right. So everybody have this memorized? Not even me. I mean, we can do the middle of the table, but not much beyond that. All right. So just to give you a scale on both sides of how it is in the real world, right? Everybody, we can imagine a millimeter, right? 1 millimeter. We have used rulers, we have used scales. We know what a millimeter is. We know what a centimeter is. So millimeter is 1/10 of a centimeter, right? Now, if you take 1 millimeter and divide it into 1,000 parts, you get what is known as a micron. Did you have a question? Okay. So we get what is known as a micron, that is 10 raised to minus 6. So 1 millimeter is 10 raised to minus 3 meters. If you take 1 millimeter, divide it into 1,000 parts, we get 1 micrometer. This is also known as micron. So if you ever hear the words micron, it refers to 1 micrometer, 1 mu m. The Greek letter mu and m, 1 micron. To give you an idea of how small a micron is, a human hair is about 50 to 75 microns in diameter. Okay. If you have used mechanical pencils, 0.5 millimeters, 0.7 millimeters, that's 500 microns or 700 microns. Now, if you take 1 micron and divide it into further 1,000 parts, you get what is known as 1 nanometer. And we are here today in the modern world, the scale, the feature sizes are approaching like 3 or 4 nanometers. The state-of-the-art machines nowadays, or state-of-the-art microchips made by TSMC, are 3 nanometers. It's that small. They're really, really tiny. Capacitors, inductors, typically on the milli and the micro range. But current is sometimes in milli and micro range. And then on the other side, talk about kilo and mega and giga, terahertz, in terms of storage, in terms of frequencies. Frequencies are typically very, very small. Sorry, not very, very, very large. Typical frequencies that we use, starting with radio communications, AM radio stations, kilohertz, FM radio stations, megahertz, right? Our wireless routers, 2.4 gigahertz, 5 gigahertz, and satellite communications are all in the gigahertz and terahertz range. There was, you can leave if you want to. I'm just going to continue on for a few more minutes. To give you an idea of how small this is, think in terms of time. How much do you think is 1 million seconds? In days, weeks, months, or years? So I heard 12 days and 3 days. It is approximately to 11.71 or something. So 12 days. He already buried the lead. Yes, 1 billion seconds is over or greater than 31 years. That's the difference between a millionaire and a billionaire. You spend $1 a second, you'll run out in 11 days. If a billionaire spends $1 every single second, it'll still take them 31 years to run out of just 1 billion. All right, we're going to stop here today and we'll pick up here again on Wednesday.